Hello Calc 3, welcome back to another video. In this video we will be starting on chapter 13 and we're going to be covering section 13.1, just the first half in this video, and specifically we will be covering the concept of curves in three-dimensional space. So in chapter 13 our ultimate goal is to combine the analytic geometry that we just covered in chapter 12 with calculus concepts that we already went through in Calc 1 and Calc 2. So we're going to start off by considering a particle moving in space. So here we're talking about three-dimensional space. You can think of it as a little dot that's just buzzing around in space. As the particle moves, it traces a curve in space. We're going to call that the path of the particle. Okay, and as the particle moves through time, we can think about the coordinates of the particle at each time t, right? So time is, I guess you can think of it as starting at time equals 0. Time is constantly flowing onward, and the particle is moving around and is leaving a path behind it. And the fact that we can talk about the position of the particle at different times gives us a way to parameterize the curve or the path of the particle in space. So we can represent the x, y, and z coordinates of the particle at different time as functions of time, so as functions of t. And to denote that, we can write x is equal to f of t, y is equal to g of t, and z is equal to h of t, where f of t, g of t, and h of t are all just different functions in terms of time. So you stick in a certain value for time and out pops the coordinates of your particle. So the point x, y, z is on the curve if and only if x, y, z is equal to the ordered triplet f of t, g of t, h of t for some t. So for x, y, z to be on the curve, we have to be able to find some time such that when we plug the time into our functions, f of t, g of t, and h of t, out pop the components of our point. But this allows us to represent a curve in space in vector form. So we can write a vector equation for the curve in space. So here we have what we're going to call the position vector, r of t, and we can set that equal to f of t times the vector I plus g of t times the vector j plus h of t times the vector k. And again, r is called the position vector of p. So the vector r in component form is going to have the same components as the coordinates of a point p. And we call the functions f of t, g of t, and h of t the component functions of our position vector r. So here's a diagram of the process that's going on the right. And you can think about it, obviously the blue thing inside of the graph is our curve that's being traced out by the particle, and r is our position vector with the initial point at the origin. And you can think about, as time is moving forward, r is going to be constantly changing so that that arrow is following the curve. So let's just say that the curve is moving in this direction. Then as time is increasing, we keep moving out this way, and the vector keeps tracing along that curve. So notice that our function, this vector valued function that we just talked about, it takes the value t as an input, and t is just some real number, but the output is not a real number. The output is a vector. And for that reason, we call these kind of functions vector valued. On the other hand, if we have a function that takes in real numbers, numbers like t, and outputs more real numbers, that kind of function is going to be called a scalar function. So scalar functions are the functions that we worried about in Calc 1 and Calc 2. And notice that all of the components of our vector valued function r up here, these component functions, these are all scalar functions. So you put in the value t and you get out a real number. Okay, so let's move right on to an example of a vector valued function and what it might look like. So we want to graph the function r of t is equal to cosine of ti plus sine of tj plus tk. And to graph it, first, let's just ignore what's going on with the k component of this function. So let's only worry about the I component and the j component. Well, if we just worry about the I component of the j component, and we assume that we have a function inside of some plane in 2 dimensions, then cosine of t and sine of t gives us a parameterization of a circle, and specifically a circle of radius 1. So just for the sake of drawing this thing, we might as well assume that it's inside of the xy plane when we're drawing. And so if we disregard that k component of r of t, we end up with a circle that I've attempted to draw in purple here in this diagram. And after we know that 2 components give us a circle, now we just want to worry about adjusting our drawing to account for the k component of our vector function here. So we're going to account for that k component of r, and notice that k is going to get larger as t increases. So the k component keeps increasing as t increases because the k component is equal to t. And after we realize this, it's relatively easy to draw what our function's going to be. So we know that if you look at it, consider yourself looking down from the z-axis, then all you would see is a circle for our function. Because if you get rid of the k component, you're just looking at the I and j component, we have a circle. But now, when you add in the k component, our function is going to keep getting higher and higher and higher up the z-axis. And so our function is going to look like this helix here. That's given in the first picture. And then these other pictures denote what happens when we change certain elements of our function. So in the second picture, notice that t in the third component, or in the k component, is multiplied by the scalar 0.3, which is going to condense everything, because for every revolution around the z-axis, all the circles that we're drawing, the step that we're going up in the z-axis is going to be smaller because we're multiplying t by 0.3. And then a similar thing is going on over here. We are decreasing the period of our 2 trig functions, which means that again we're going to go around the z-axis faster, even though this time we're going up the z-axis at the same speed as our original function. Okay, and from here we're going to take a relatively different turn, and we're going to move into limits and continuity of the vector valued functions that we just defined. So recall that for a real valued function, and here I'm going to denote that function f, and you might have not seen this notation before, but this just means that it's a function f that takes real values and outputs real number values. And for these kind of functions in Calc 1, we gave an epsilon delta, this should not be proof, but epsilon delta definition for the limit of f approaching some value. And now we're going to give a similar definition for vector valued functions. So remember that in Calc 1, the limit was the bread and butter of calculus. It's kind of the foundation on which everything is laid. And so if we want to build a calculus on vector valued functions, we better do the same kind of thing. So if we let r be some vector valued function, and we let L be some vector, we say that r has limit L as t is time here, approaches the time t naught, and we write this expression here, which should be familiar from Calc 1. It's the same kind of notation. So we have the limit as t goes to t naught of our vector function r is equal to L if for every epsilon greater than 0, there exists a delta greater than 0 such that whenever the absolute value of t minus t naught is between 0 and delta, it implies that the length of the vector r minus L is less than epsilon. And ultimately, we don't really need this definition for the course. So if, as I went through that, it seemed very foreign, that's absolutely fine. I just want to give it because I'd feel a little bit bad if I didn't give the definition. But realistically, we're never going to use the definition. You're not going to be doing any epsilon delta proofs for limits. This is really the important information that you need to know for the course, is how to calculate the limit of a vector valued function. So if we have a vector valued function r again, and the limit as t goes to t naught exists for each of the component functions. So remember that the component functions are this f of t, g of t, and h of t. So assume that the limit exists as t goes to t naught for each of those component functions. Then the limit as t goes to t naught of our vector valued function is going to be equal to the limit as t goes to t naught of each of our component functions with the appropriate standard unit vectors kept next to them, right? So when we want to take the limit of a vector valued function, it's sufficient for us to just evaluate the limits component-wise. So we find the limits of each of the component functions, and that'll give us the limit of the vector valued function. And let's go right into an example of this. So we're going to take the same vector that we had from the previous example, or the same vector valued function. This r is equal to cosine ti plus sine tj plus tk. And let's say we want to find the limit as t goes to pi over 4 of our vector valued function r. Then we're going to take the limit as t goes to pi over 4 of cosine t, which is just going to be cosine of pi over 4, and we leave this the standard unit vector I there. Now we're going to take the limit as t goes to pi over 4 of sine of t. That'll give us the sine of pi over 4. And then the limit as t goes to pi over 4 of t is just pi over 4. And so the limit as t goes to pi over 4 of r is equal to cosine of pi over 4i, which is equal to radical 2 over 2i, plus radical 2 over 2j, plus pi over 4k. So again, when you want to find the limit of a vector valued function, you just find the limits of the component functions that compose our vector valued function. Now recall that in Calc 1, almost immediately after we introduced the topic of the limit, we introduced the topic of continuity, and we're going to do the same thing here. So now we have the concept of a limit for vector valued functions. We also want to have the notion of continuity for vector valued functions, and it's just as intuitive as our generalization for the limit. So if we have a vector valued function r of t, this function is continuous at a point, which I'm going to call t naught, if the limit as t goes to t naught of r of t is equal to r of t naught. And this is almost identical to the definition of continuity for scalar functions that we gave in Calc 1. Also, r of t is continuous over an entire interval I if r of t is continuous at all the points t that lie inside of the interval I. So r of t is continuous at a point t if and only if all of the component functions are continuous at t. So to find the limit for our vector function r of t, we took the limit of the components, and now I'm saying that to show that a vector valued function is continuous, we just have to check that the component functions are continuous. So let's give an example. Again, we're going to take the same vector valued function we had before. So r of t is equal to cosine ti plus sine tj plus tk. And this vector valued function will be continuous for all real numbers t because we know that the component functions, cosine of t, sine of t, and t, are all continuous for all real numbers. On the other hand, if consider the scalar function f of t is equal to the floor of t. If you don't know what the floor function is, this is the function where you can input any real number and it will output the integer that is directly below that real number. So for example, if I wanted to see the floor of 2.3, this would be equal to 2. So it goes to the closest integer that is less than or equal to the number that we input. But this function is not continuous at any integer. So any vector function with the component function being the floor function is not going to be continuous at any integer. So for example, if we took our vector valued function from above, the r of t, but we replaced the k component, instead of being t, we replace that with the floor function of t, we would now have a vector valued function that is not continuous. Okay, so that's the end of the material for the first half of section 13.1. A video with the second half of section 13.1 will be coming up shortly.